Hello everyone and welcome back. If you remember last time, we defined how exactly our neural network works and why it works that way. In the end, we kept track of these four variables, AL, BL, ZL, and WL, where the first three were column vectors and the last one was a matrix, and L stood for the layer we were referencing. We also derived these two nice looking equations, which dictated how the entire network works. The sigmoid function right here was simply a way of getting our network outputs to range between 0 and 1. In this video, we will learn about how backpropagation and gradient descent work together, which is the essence of the algorithm that lets machine learning happen. We will then code this into existence and give it a test. This video contains some very delicate information, and I encourage you to sometimes pause and try to figure out what I'm about to derive, or play around with the equations and get a feel for them on your own. Getting hands-on is important to understanding. That being said, let's get started. First off, it's great that we have a network, but it's not really that useful right now, since most of the time it'll be incorrect, since our weights and biases were randomly initialized. It helps to keep a specific example in mind. Imagine we have this 5 by 5 grid here, alright? And we want to see if the grid displays an X or an O. Now, I know this doesn't really look like an O, but there's only so much 25 pixels can do. Anyway, this means our network will have an input layer with 25 neurons for each pixel, and then some hidden layers, and then 2 neurons, where the output of the first neuron would represent how confident the network is, with an image being an X and the second neuron in O. What we need to do is figure out a way to adjust the weights and biases to make the network do better. And to get there, we first need to define how bad the network is doing. For example, if the network had an activation of 1 for X and 0 for O, but the image was of an O, we would give it a bad score. We know the correct output would instead be a 0 followed by a 1 instead. One way we could put a number to the badness or cost of a neural network is sum over the difference between the outputs and the correct outputs in the last layer. And this would get you this equation right here. Here, C stands for a function that represents the cost, or the cost function. Capital L denotes the last layer, and Y denotes the correct output. This works fine, but we can still make it a bit better. If the network is pretty close to the right answer, it makes sense to punish it less, and if it's way off, it makes sense to punish it more. We can do this by taking the difference as we did before, but then amplifying the effect by squaring it. We also tack on an extra 1/2 at the end to make our life easier on later on. This idea gets you this equality right here. And on the very right, we have a way to write this using linear algebra. If the connection between these two expressions doesn't make sense immediately, notice that taking the magnitude of a vector is the same thing as taking the square root of the sums of the individual differences squared. Now, one important thing to notice is that C tells us the cost when given an input activation and the correct output activation. Those two things are being given to us, and what that means is that C is a function of just the weights and biases. And that means that to improve our network and get better weights and biases, we can just find the values of them that minimize C. Now, that's a great revelation. However, minimizing something with all these variables is kind of intimidating. Instead, let's think on a smaller scale. Imagine we have a two-dimensional vector v, and C takes in v instead of the weights and biases. If we look at some small change to C, delta C, it can be well approximated by the partial derivative of C with respect to the first component times the change in the first component plus the same thing but with the second component. Alright, and remember, the partial derivative is like taking the derivative but treating all other variables as a constant. Intuitively, each term simply tracks how the individual component affects C, and then, by adding them up, we get the total change. Moving on, remember that the gradient of a function is just a column vector containing all these partial derivatives, and that delta v is just a column vector containing all the changes. Using this, we can write delta c in a much more compact way. And notice that this expression generalizes to V having even more components than just 2. Now remember, our goal was to minimize C, and this means that if we can figure out how to make the change in C, which is delta C, negative, that means we're going a step in the right direction. And also remember that we're minimizing C by changing the weights and biases. And for us, delta V represents that change. Seeing that gradient of C in the project and knowing that we're changing C makes us wonder if setting delta V to be equal to the negative gradient of C works. Substituting this value in gets us this. Notice that the magnitude thing comes back here, so once again, make sure you see the connection. Since anything squared is greater than 0, we have found a way to make sure that delta C is always negative. At least almost always negative. Remember that this is just a really good approximation for delta C, and that the smaller V gets, the closer we get to them being equivalent. To try and get some control over this, we introduce a new variable, eta, and make V equal to the opposite of eta times the gradient of C. We can think of eta as being a learning rate because delta V depends on our choice of eta. Now, as of now, you might realize something. Our algorithm doesn't just find the optimal weights and biases instantly. Instead, you apply it iteratively, and then it converges onto the correct values. You can think about it like trying to walk down a hill with fog all around you. Even though you can't see the bottom, you can see which direction is downwards, and take a step that way. And by doing this over and over again, you will eventually reach the bottom. And that's exactly what gradient descent is, a way of reaching our bottom. With that out of the way, all that is left is to find the gradient of C. Since C depends on the weights and biases, it doesn't make much sense to continue on with V. So now we'll switch back to using our original C, which took in the weights and biases. The gradient of C contains these partial derivatives, so that is what we aim to find. Backpropagation is the fast algorithm that enables us to do this. The main idea is that instead of passing information forward through a network, we pass it backwards. We backpropagate. To see where it comes from and what it is, it helps to introduce an intermediary quantity, delta L sub j, which will represent the error in the jth neuron in the lth layer. By error, I mean the amount that the weighted input ZL sub j needs to change to make the network's final output correct. Now let's imagine that the change needed is ZL sub j. Since that's the only quantity that's being changed, the overall difference in our cost function will be this expression right here. Using a bit of manipulation, we can get that the change is well approximated by this expression right here. Now, inspecting this expression, if the partial derivative is small, then we can't really improve our cost function that much without making delta ZL sub j too large, which isn't useful. And if the partial derivative is large, then we can have a good effect on the cost function by simply making delta ZL sub j be its opposite. And in this sense, it's almost like the partial derivative is a good measure for the error, since it shows us how much we can help the cost. And for this reason, we make delta L sub j be exactly that, the partial derivative. Now, we are ready to find the partial derivatives of the cost function with respect to the weights and biases. Let's start with the bias. We apply the chain rule to the partial derivative and introduce a ZL sub j there. You might be wondering, why ZL sub j? Well, remember, we defined the error as this exact term, so it'll become useful later on. The second partial derivative is straightforward. The first term goes away, and when you differentiate BL sub j with respect to BL sub j, you just get 1. So everything boils down into this very nice equation. We can also write this using linear algebra to simplify things further. Make sure the connection makes sense. Moving on to the weights, it's the same deal. The second derivative, once again, we use our definition of the error to simplify the first partial derivative. The second derivative is the only thing that changes. Since now we're differentiating with respect to the weights, the bias disappears, and the only term that remains in the summation after differentiation is a term containing the WL sub jk. What remains is the AL minus 1 sub k, and that gets us to this nice equation. Writing this with linear algebra gets us this even more compact form. Now, if you don't see the connection between these two equations immediately, pause right here and see if this explanation makes it clear. Now, before you call it done, remember that we still don't exactly know what the error is. So first, we find the error in the last layer. Notice how we use capital L, meaning that we're working with the last layer. Before, we use ZL sub j as our intermediary. However, since we can't do that now, we use AL, since that's directly present in C. Here you see why the 1/2 was introduced. After differentiation, it makes things easier. And also, when we differentiate, all the other activations go away, and we're left with just the difference between the original two. With the second partial derivative, remembering how we even get AL sub j makes things pretty straightforward. And after the dust settles, we get this nice looking equation right here. It's important enough to note this generality because, as you might have guessed, we can use different cost functions, and this helps us generalize to that. And of course, we have our compact linear algebra representation right here. The only thing to note here is the use of the Hadamard product, which simply means do element-wise multiplication. For example, if I took the Hadamard product of these two vectors, I would get this. If you still don't understand why we use the Hadamard product, pause here until it makes sense. Finally, now that we have the error in the last layer, we apply some sort of induction and we find the rest of the errors by relating them to the error one layer ahead of it. This time, the chain rule is a bit more involved since the previous neuron has an influence on a bunch of neurons in the next layer. So we sum over all those neurons. The first partial derivative isn't too bad. We once again use our definition of the error. In the second partial derivative, after rewriting the equation to include ZL sub j, it's easier to see that all the other terms go away after differentiation, and all that we're left with are these two terms containing W and sigmoid prime. And that leads to this equation. In this case, the compact form makes things a bit easier to understand. We're just transposing the weight matrix and applying it to the errors in the next layer. The connection between these two equations, however, might not be obvious. It helps to visualize it. As you can see, we're just backpropagating the error in the last layer to get the error here. The Hadamard product is used for similar reasons to the last equation. And as for the combination of how the weights and the errors can lead to this, pause right here and see if this helps you figure that out. With that out of the way, here are the main equations we came up with. First, the way our network moves information forward. Then we figured out what gradient descent is and how we move towards the lower cost. Finally, how we find the gradient of the cost function with backpropagation. I think you can agree with me on this. Although the equations are involved, they're not too bad and the math isn't too difficult. And it's crazy that these 8 equations describe how we can make machines learn. If any of these equations don't make sense, make sure you understand where each of them come from. All improvements to this algorithm stem from understanding it. That being said, let's code it. First, we define what exactly sigmoid and sigmoid prime are. You might see the tan h right here and wonder why it's there. The expression is still the same, and it still evaluates to our sigmoid function. It just helps with stability in the program. Read these comments for a bit more information. Continuing, we use the same network code from last time, the only difference being that we keep track of the amount of layers that we have. After that, we write down our gradient update. Notice how we use this backpropagation method to find the gradient. After we have the gradients, we just put these two equations into place and into code with this right here. And now we create our backpropagation method. We first initialize everything that we have to remember. And then we perform the forward propagation, but this time keeping track of what the activations are and what the z-values are. Notice that the activations will have more. Notice that the number of elements in activations will be one more than the number of elements in z-values. And that's because activations also contains the input layer. With all the forward propagating done, now it's time to backpropagate. We start by calculating the error in the last layer with this equation right here, and then we use our equations to find the partial derivatives with respect to b and c, with respect to b and w, to find how much we changed the bias in the weights. After getting the last layer's error, we just find the errors of all the rest of the layers using this right here. Notice that the equations to find the gradient bias and gradient weights are the same, but we just changed the equation for delta because now we've switched to this equation. We also insert it in the first position of the list because we're going backwards. And once we're done with that, we just return all the gradients that we have. And that's it. In 56 lines of code, you have a machine learning algorithm from scratch. To test it out, we first need to turn the images, which are 5 by 5 arrays, into column vectors with 25 entries. After that, we initialize our network with the layer size we decided on. You can see that at the beginning, our network doesn't really understand what's going on. It's putting a lot of emphasis on O. To train our network, we just make an update towards the correct values for both X and O 1,000 times. Notice here that our eta is 0.2, but you can change it and get different results as well. Now, if we feed forward, our network has pretty good results. It's correct. Now, you might wonder what the point of all of this is. Couldn't we have just created an if-else statement to check whether it's an X or an O? It's because when we give a network the training data, we don't hope for it to just learn the training data. We want it to be able to generalize and to be able to deal with changes that a hard-coded AI wouldn't be able to handle. To make this concrete, here's a new O, something that's not the same as what our network had seen. If we see what our network thinks, it's still relatively correct and still believes it's an O. That being said, for the sake of not throwing too much information at once, this network is pretty basic and still can be very much optimized. In addition, we only give our network 2 samples to train from. In future videos, we will make this a lot faster, give it more training data, and use it to solve problems like recognizing handwritten digits. Great, that's it for this video. In the next video, we will learn about stochastic gradient descent and how we can monitor our network's progress. If you learned something from this video and are converging towards helping me out, please like and subscribe. Thanks for watching.